So we are discussing about the three-phase distributed winding, and let us consider a very simple three-phase distributed winding, which each phase having a single coil, and there are 6 number of slots. And since it is a two-pole winding we want to make, so coil span will be 180 degree electrical all the time, but in this case it will be 180 degree mechanical as well, because this. So how this winding was made, I will just quickly go through. Suppose these slots I am not drawing for clarity's sake. The conductors are in these slots. Slots I have not drawn here. So suppose in this slot R1 conductor is present. Its return will be diametrically opposite R2. This is one coil. And as you can see, if current enters through R1, like this one cross, this one dot, then the field will be produced in this direction, in this R1, R2 coil. So the symbolic representation of this coil in this diagram can be made like this. Okay, R1, R2, and when this coil carries current, it produces field along the horizontal line, R1, R2, this current. And when current enters through R1, field will be produced radially outward direction, as can easily be seen in this direction. Suppose R1 is cross, this is dot, field will be along this line. Similarly, Y phase, so this R phase coil we place, then after 120 degree we start with Y phase coil. Y1 is placed in this slot and its return will be diametrically opposite Y2. And once again, the magnetic axis of Y1, Y2 will be perpendicular to the line joining Y1, Y2. And when current enters through Y1, that is, this is cross, this is dot, field will be along this line. So this is this line. So when current enters through Y, field will be produced once again along the radially outward direction. And finally the B phase coil, which is 120 degree apart from the start of Y phase coil, and it will be like this, and its field direction will be line perpendicular to B1, B2 along that line, and if B1 is cross, B2 is dot, the direction of the field will be like this. So when current enters through B1, the field direction will be all radially outward direction. That is what we did. Then what I was trying to tell, suppose these three coils, they are connected in star and supplied from a balanced three-phase source of voltage, such that the currents are IR, IY, IY and IB. Balanced three-phase current is flowing. And let us assume that IR is equal to some current I max sin omega t. IY is I max sin omega t minus 120 degree, and IC RYB is I max sin omega t plus 120 degree. Now what we want to find out, we know that last time I told, if there were a single coil, R1, R2 is present, suppose B1, B2, Y1, Y2 are not present, and if that coil carries a current, then the field distribution along the air gap of the machine is strictly rectangular in nature. It will be rectangular in nature for a single coil. However, suppose that waveform is Fourier analyzed and only the fundamental component we are thinking of, then the field distribution will be harmonically varying along the length of the gap. And when the current in the coil is alternating in nature, we get for a single coil a standing pulsating waveform. Now when all the three coils carry balanced three-phase current, then what happens to this field we want to find out. So we will be doing like this. So suppose these are the current. Now you consider at least two instants. Suppose you consider the instant omega t equal to 0. At omega t equal to 0. That I did slightly hurriedly. Obviously IR will be 0. And IY will be minus root 3 by 2 I max, and IB will be root 3 by 2 I max. This will be the currents. So in this diagram, if I put these values of the current, we find that IR is 0, so there is no current at that time in the R phase. Y phase it is negative. So current is actually entering through Y2 and coming out from Y1. So Y2 I put cross and Y1 dot here. And similarly B phase coil current is positive. That means really through B1, that is IB is positive, means really it is entering through B1. So this is cross, this is dot. Now, as you can see, the resultant field, without doing any vector addition, we can say it will be vertically along this line, because these two conductors can be grouped together, which are carrying cross current, and the direction of the lines of force will be like this. And here also these two conductors can be grouped together and carrying dot current, so here it will be like this. So this set of three-phase coil at omega t equal to 0 creates a field such that if you call this side north, this will become south. Lines of forces will be like this. This is omega t equal to 0. Now this also we can get from this phasor, this one. Suppose take the case of Y phase. Y2, current is entering through Y2. Therefore, the field produced by Y phase, in which direction it will be? In this coil now, so it will be like this. If through Y1 current enters, the field is produced along this direction. If through Y1 current enters, but current is entering through Y2, actual current direction I know, so it will be along this line only, axis, but it is now in this direction. And what is the magnitude of this one? This will be proportional to some K into N into I max root 3 by 2, that is root 3 by 2 K into this one. This will be the direction parallel to this axis, this Y phase. Similarly, B phase, through B1 current is entering, so it will produce field really in this direction. So there will be field produced in this direction in the air gap like this. And what is the magnitude of the field? It is K into root 3 by 2 into Ni max. So the resultant field will be just vertical in this direction. The addition of these two phasors in space at omega t equal to 0. And obviously this angle is 60 degree and these two phasors are equal. So the resultant will be, as you know, 2 into root 3 by 2 into K into N I max into cosine 30 degree. That is two phasors, PP magnitude, angle between them is alpha, 2P cosine alpha by 2 is the resultant. So this one, if you calculate by putting root 3 by 2, so resultant magnitude will be this one. If I write here, this will be root 3 by 2 cancels here, and another root 3 by 2 comes here. So this will be 3 by 2 K N I max. This will be the strength of this resultant field at omega t equal to 0. It is acting vertically downwards. Now consider another instant, say omega t equal to, time has passed now, suppose time has become omega t equal to 60 degree, such that IR, now there will be some IR will be I max sine 60 degree, that is plus of root 3 by 2 into I max. IY will be, if you substitute there, this will be minus root 3 by 2 into I max. And IB of course will be 0 because sine 180 degree is 0. So B phase will not carry any current. So the conductors are, once again I produce the same thing here. R1, this is R2, this is Y1, this is Y2, and this is B1, this is B2. And now from this one I put cross dot in several conductors. So IR is positive and current is entering. So through R1 current is entering really, and through R2 current is coming out. B phase does not carry any current. Y phase, now minus current flows. In the Y phase minus current flows. That is, IY is in this direction, and that is negative, means actually current is from capital Y to capital Y1. So capital Y to capital Y1 means this will be cross and this will be dot. And here once again these two conductors can be grouped to find out the field along this line, cross here. So this, and these two can also be grouped here, and this will be like this. So compare the field pattern with the earlier case. At omega t equal to 0, field was like this. Some time has passed. Field has, this was say some north, this was south. That north-south thing has moved by some angle. By what angle it has moved? Once again, from the symmetry it appears it will be 60 degree. And this of course we can verify by once again adding by vectors. For example, in this case, IR is positive. IR is positive means current is entering through R1. So field will be produced for R phase along this line. In this particular instant, it will be along this line. And what will be the magnitude of this one? Some K root 3 by 2 N into I max for R phase, because current is entering through R1. It will be away like this. B phase does not carry current. However, Y phase carries current and it produces field along this line. So this Y phase field will be here. Y phase field will be here. And this angle will be once again 60 degree between these two. And this will be K root 3 by 2 into N into I max. And the resultant, once again, if you find out, it will be this 3 by 2 K N I max. So the resultant field, which was vertically downwards, that is here, it was earlier at omega t equal to 0, has now moved by this angle. And this angle was 30 degree. This was 30 degree with this vertical. So it has moved by an angle of 60 degree. Therefore, with time omega t equal to 60 degree, it has moved by 60 degree. In this way, you take any omega t, say omega t equal to some very unusual angle, say 17 degree, because 60 degree, 30 degree is some usual angle. Even if you take that and find out the MMF produced by each of the phases and add them vectorially, you will land up with this same resultant 3 by 2 into N into I max. Of course, as a just mathematical proof, you can do it in this way for any arbitrary position like this. This of course I will not do, I will tell you how to just do, you can try. What I am trying to tell, this is the R phase winding. This is very simple and easy to understand. This is Y1, Y2. Y1, Y2. And this one is, perhaps many of you know how to deal with such a situation. Suppose this current is IR. This current direction I will assume. At any time, suppose this is IR, this is IY, this is IY, this is IB. I will not bother about the exact value of the current. The direction I will always maintain like this. The exact direction of the field will be taken care of by the reversal of the sign of the current, etc. What I mean to say, suppose IR flows through this one. In which direction field will be produced? In the radially outward direction. So R phase will produce a field along this line. What will be its magnitude? Its magnitude will be K into N into IR, instantaneous value of the current. At any time I am doing now. Forgetting about omega t equal to 30 degree, 60 degree, just to give a general proof sort of thing. So K into N into IR will be the field along this direction. Now you may argue, what will happen if IR changes direction? That is taken care by this equation. When IR will become negative, this means a phasor drawn in this direction with a negative sign means a phasor in that direction. So I am not making any mistake in that way. Similarly, IY will produce a field along this line. This will be some K into N into IY. Of course, at any point of time, these two lengths may not be equal, because at that time currents may be different. And B phase will also produce some field here along this line, K, N into IB. I want to find out the resultant field. So what you should do is this. You consider, just some vector addition. You consider this to be, suppose this to be your x-axis, x-axis, and this to be your y-axis. You have to add these three vectors whose directions are known. Completely magnitudes, of course, depends upon instantaneous values. Then what will be the resultant of these three? How will you do? You find out the component, x component of all the three vectors. So F resultant, x component of resultant MMF or field, resultant field, will be what? K into N into IR plus the component of this one, that will be what? Minus K N into IY into cosine 60 degree, that is half, into half, and minus K N IB into half. Now I can substitute IR, IY, IB as I max sin omega t minus 120 degree, etc. So it will come as a function of time, and it can be easily simplified, some small form. So this I will find out, x component of the resultant field. Similarly, I will find out the y component of the resultant field. That will be, of course, x cannot have any component along this line. So y positive I have assumed there. So this is 60 degree. This is also 60 degree. So this will be K N I B into sine 60 degree. That is root 3 by 2 minus of K N I Y into root 3 by 2. There also I will substitute IB, IY. They will become function of time. Omega t thing will be there. Then what you will do to find out the resultant? Under root this squared plus this squared you do. And you will find this is coming out to be that 3 by 2 K into NIR. So this shows that the resultant field, strength of the resultant field at any instant of time will be, in fact, indeed, this 3 by 2 K N I max. And magnitude is constant, resultant field magnitude, and it is rotating in space. So some sinusoidal B field is moving. At what speed it is moving? It is moving at a speed same as the supply frequency. When omega t has become 60 degree, field has moved by 60 degree, like that. And two things are important. So a constant magnitude field will move at a constant velocity has been produced. But what is the direction of this field? In which direction it moves? It moves in a direction along the R to Y to B, in that sequence it moves. What I mean to say, the field will be moving, as we have seen in this particular case, in this direction. Is not? Anti-clockwise direction it is moving, because omega t equal to 0 I have considered. It was vertically downwards, then it has moved to the left. Therefore, it is moving in this direction. I mean clockwise direction it is moving. Now, to understand why, with respect to this naming here, I will say it is moving along R1, Y1, B1 or R2, Y2, B2, whichever way you go. In fact, this direction, do you think, can it be reversed at my will? By doing what? By changing the supply phase sequence. That I leave it as an exercise to you. Suppose this supply phase sequence here I have assumed RYB. RYB. Suppose two supply terminals you interchange. That is, IR will be suppose I max sin omega t. Actual this Y winding current will be then sin omega t plus 120 degree. This I can easily change, because the winding axis etc. they are already fixed. That I cannot do anything. So only to the Y phase I can pass, of course, current which will be 120 degree led by the R phase current. That depends upon this one. So like that, in that case, IR, if you assume I max sin omega t, IY will be I max sin omega t plus 120 degree, and IB will be sin omega t minus 120 degree. Getting this B phase. And then once again considering omega t equal to 0, omega t equal to 60 degree, like that, you can easily show, okay, in this case also strength of the field is same, 3 by 2 K N I max, and it will be moving along the anti-clockwise direction. This can easily be shown. Therefore, direction of this field, which is rotating in nature, can be reversed by simply changing the supply phase sequence. And another thing I would like to tell, whenever you tell about the speed of something, we must say with respect to what. This will become very much important in understanding induction motor principle operation. So at the very first stage, you should understand what do I mean by the speed with respect to what. I mean, by that term, what do I mean? It means that the speed of this field, whatever will be produced in this particular case, will be, you please write down the speed of this field. The speed of the field is omega, or say F, so much rotation per second it will do. Direction of the field decided by, whether clockwise or anti-clockwise, decided by supply phase sequence. And the speed of the field, once I say it is F, I must add to it that the speed of the field, speed, that will be more correct, of the field, with respect to what should I write? With respect to the structure, which houses the winding. This is important to note. For example, this is, suppose these 6 coils. These 6 coils are on the rotor of a machine. Rotor is stationary. Rotor is not moving. I am not considering any machine as such. Suppose you are on the rotor, you have got these 3 coils, 6 coils, or 3 coils, 6 slots, and you have got windings energized with 3-phase source. So the speed of the field with respect to a stationary observer, that is with respect to this rotor structure, is this much. Now you can supply this 3-phase winding, and also you can rotate by suppose some external means the rotor at some RPM with a say prime mover. Are you getting? Suppose the rotor is moved externally at some speed, and the 3-phase winding is also energized with balanced 3-phase supply. Then with respect to a stationary observer, the field of the speed will be how much? It will be, if the rotor rotates along the same direction as that of the field with respect to a stationary observer, it will be the rotor speed plus the field speed. And if the rotor rotates in the opposite direction, then to a stationary observer it will appear to rotate with the difference of the speed. So this will come often in the analysis of this one. Now what I will tell you about the some 4-pole basic windings. Suppose 4-pole windings and its comment on the, suppose 4-pole winding you want to do. 4-pole 3-phase balanced winding, which is elementary winding, but it gives you a feel what is there. Elementary 4-pole 3-phase balanced winding. Now in this case, suppose you have got 12 slots. 12 number of slots are there. That is, angle between these sectors is 30 degree. Each sector is 30 degree. And there are several slots. That is slot 1, 2, 3, 4. 12 slots are there. Now I am starting to make a 4-pole winding. Remember, in a 2-pole winding, that is just to remind you that suppose given a winding, the winding has been wound for you, and suppose you want to examine for how many poles this winding has been wound. How will you test it? Suppose this winding layout is before you, R1, Y1 like this. You simply consider a single phase coil that is concentrated on say R phase. This is a coil. One way of looking at it, the coil span is 180 degree mechanical. So it is a 2-pole. Or whichever position the coil is present, you energize that coil with DC current. You imagine all 3-phase business you forget just to examine whether it is a 2-pole, 4-pole or 6-pole. So you energize that R phase coil and see how many poles will be produced. Suppose only R phase is energized, and this cross, this dot, whatever it is. So this will only produce 2 poles. And 2 poles will be produced by Y phase and B phase also, and their resultant we are finding out, and ultimately giving you 2-pole resultant field. Now similarly here we will see how a 4-pole winding can be wound. There are 12 slots. So let us start with R phase winding. I will be going slowly, but very simple it is. Suppose I will not once again draw these slots. Slots are here. Suppose I put R1. Where should be the return of this coil should be placed? Here? Here. It should be placed here. You are correct. Because it is a 4-pole machine I want to do. So coil span must be 90 degree mechanical. Of course, this is 180 degree electrical. That is separate thing. R2 will be there. So R phase 1 coil is placed. Now I must start with the Y phase winding, which should be 120 degree electrical apart from the start of R phase. So where should I place this Y1? So first, second, 60 degree here, mechanical 60 degree. So this should be Y1. Where should be its return? 1, 2, 3, 90 degree. Its return should be here. If I am wrong, correct me. Then B phase starting should be 1, 2, 120 degree. So this B phase will start from there, B1. And B2 will be 1, 2, 3, it is here. That is, I have put some one coil R1, R2, Y1, Y2, B1, B2. Then I find several slots are still to be filled. What you do, I mean, without not going into much, you start here once again with R phase. Another coil you try to fill up. That I will call it R1. That I will call R1, small R1, and its return will be 1, 2, 3, R2. I will tell you what it is all about. So another R phase coil you put. From this point. Then Y phase coil, another Y phase coil you put. It will be 120 degree apart from this one. So this will be small Y1 and 1, 2, 3, small Y2. And another B phase coil you put, small B1, 1, 2, 3. And now the things are filled up. Now that is what has been done is this, that is this R phase coil, you have got two coils in the R phase. One is marked with R1, R2 and another is marked with small R1, R2. And you have got another Y phase coil, capital Y1, Y2, two coils are there and small Y1, small Y2. And for B phase also this capital B1, capital B2 and small b1, small b2 are there. Now what you do, these coils, suppose free terminals are available to me externally, I will connect them in series. I will connect them in series. And this I will connect in star, this winding I will connect in star. And once again give three phase supply to this IR such that at any instant current is IR, IY, IB, like this. Like this I will do. Now suppose once again you just consider say omega t equal to 0 degree. Omega t equal to 0 degree, R phase does not carry any current. R phase does not carry any current. Y phase current is minus, say at omega t equal to 0 degree. Once again IR is 0. IY is minus root 3 by 2 I max. And IB is plus root 3 by 2 I max. So those current directions I show in this diagram. So IR 0, but IY is negative. That means through the Y2s, current are actually coming out flowing here from right to left, since IY is negative actually. So through 2s of Y, currents are entering. That is Y2 here and small Y2. And through the 1s, currents are coming out, capital Y1. By virtue of the way I have connected, it will be like this at that time, omega t equal to 0. This is Y current. B current is positive and equal strength. So actually through B1s, B1, capital B1 and small b1 current is entering. So I will put cross there. So B1 here, small b1 here. And through B2s currents are coming out. Now in this case, if you can group these two coils because they are carrying cross current, so it will produce a field in this direction. These two can be grouped at omega t equal to 0, of course. This will be like this. Once again, these two can be grouped here. This will be once again like this. And you can have this one. So you can easily see 4 poles have appeared. Because if you call this to be lines of force coming out, if you call this to be north, lines of force entering here, this will be south, this will be once again north, this will be south. 4 poles have been produced. And this is at omega t equal to 0. Now, I will not do that vector addition, etc. But what I want to tell you, what do you think the resultant field, suppose here, it will act vertically downwards? Nah. This is symmetrically placed. This, here, the resultant as if will lie vertically downwards. Now consider the instant omega t equal to 60 degree. Omega t equal to 60 degree. This time you remember IR is positive. IR is root 3 by 2 I max. And IY is minus of root 3 by 2 I max. And IB is 0. IB is 0. Therefore, here once again I show the conductors. This is suppose this conductor I draw inside because no space is available. This is another conductor. This is this. These are the conductors. I will quickly fill up with those names. This is the second diagram below. And call them, this is R1, this is small b2, I will just fill up like this. This is Y1, this is capital R2, this is capital B1, this is capital Y2, this is capital Y2, and this is small R1, this is capital B2, Y1, R2, B1, and this is small y2, this one. Here once again you can show the direction of the current. IR is positive, so through R1 current will be entering. So I should put a cross here. R1, all R1 will be positive. Where is the other R1? This one, R1. And R2 will be dot. This is dot, this will be dot. Y is negative, that means through Y2 current is entering. So current will be entering through 2's, that is this one, Y2 cross, Y2 cross, Y1 dot, capital Y1 dot. Here once again you can group these two cross currents. This will be like this here. This can be grouped, this can be grouped, this can be grouped, this can be grouped. So the arrows also I can put. This is cross like this. This is dot. So this will be the arrow. Cross. And this will be dot. It will be like this. And B phase do not carry any current. Now although I have drawn it like this, these are, just tell me with this one, along which line the resultant will be acting. Imagine this to be just center, I mean not correctly drawn. This one is 30, this is also 30. So along which line it will act? It will act along this line, this resultant field. From symmetry, because these magnitudes are same here, it will act along this line. Now, what I want to say, in this way, if you go on choosing different instants and try to show the actual direction of the currents and try to have some idea about the direction of the resultant field, etc., you can find it out. But here, one thing you note, that at omega t equal to 0, it was like this resultant. At omega t equal to 60 degree, it will be like this. So, by what angle it has moved? Only 30 degree it has moved. No, 30 degree mechanical it has moved. I should say it has moved by 30 degree mechanical. But in the first case it was not like that. At omega, when omega t changes from 0 to 60 degree, your resultant field also moves by 60 degree mechanical. Of course, there was no difference between mechanical and electrical degree because it was two pole. But now we find the mechanical speed will be slightly lower. It will be lower. I will tell you about this speed much more, but I want to tell about this fact, why these things were filled up once again. What is the idea behind that? If you look at this diagram, what I want to tell is this fact. Although it has become cumbersome. Now, what I would like to tell, this is a two-pole configuration. This you can see now, both these diagrams. So, this is a two-pole configuration, and this is a six-pole configuration. Now, you start from, look at the pattern. This R1, B2, Y1, R2, B1, Y2. This is how the numbering is coming here. Now, you start from here. R1, B2, Y1, R2, Y1, B1. So, it is what I want to tell, this whole thing coming here over 360 degree, that is Y2 once again R1 is coming here, it is now packed into 180 degree mechanical. And once again, our next 180 degree also same thing, R1, B2, Y1, R2, B1, Y2. So, in this sense, what I want to say, that you have, suppose the developed diagrams here, if you, so over a 360 degree mechanical angle, these patterns were maintained, R1, B2, Y1, R2, B1, Y2. And once again, it repeats with capital R1, because it is developed diagram like this. It is for a two-pole configuration. Now, over the same angle of 360 degree mechanical, suppose this is 360 degree mechanical. It is somewhere here is the middle, 180 degree. Now, over this 180 degree, this pattern, this R1, B2, Y1, R2, B1, Y2, R1, and once again in this one, the same pattern repeats. Are you getting? So, therefore, the distribution of the MMF, there will be 4 poles produced. This set will be producing 2 poles, this set will be producing 2 poles, and you will be getting once again a revolving field like that. Remember that to analyze a machine, whatever be the number of poles, 2 pole, 4 pole, 6 pole, whatever it is, you should concentrate your attention what is happening under 2 poles. Rest of the poles, it will be exactly repeating in the steady state case. So, it was for that reason it was filled up. In fact, after knowing this result, we know somehow I have to accommodate the same pattern in 180 degree first mechanical, that whatever came in 360 degree mechanical in 2 pole configuration for a 2 pole machine. If it is a 6 pole machine, this pattern, same pattern is to be repeated, I mean divide into 3 like that, and these pole pairs will come. You getting? So, this you should remember. Now, I will tell you about the consequence of this particular study of this rotating field. I will not do any mathematics today. That is, now what is this importance of studying this one? See, you can produce a rotating magnetic field by simply rotating a magnet, north south. You rotate by mechanical means, it will give you a rotating magnetic field, B distribution, whatever it is, it will go on rotating. Now the important thing is, here you are producing a rotating magnetic field once again, but with the help of stationary coils. There is no moving part. You simply energize it with a three-phase supply, and whatever effect this field will produce, similar effect you will get by energizing three-phase coil. Now, what is the magnitude of that field speed? Let us write down. That field speed magnitude, mechanical speed I am writing, mechanical speed. You tell me, mechanical speed. And let us write in, suppose, RPS first, let us write RPS. For a two-pole machine, it will be how much? Equal to F. Now, as a general, I want to write, suppose P is the number of poles of the machine, P equal to number of poles, twice F by P, so much of RPS. And this is, mind you, the mechanical speed of the machine. And this is the speed of the rotating field in mechanical means, mechanical speed I mean, if you could measure it with, of course, field speed cannot be measured with a tachometer, but that sort of thing in what physical rotations it makes to F by RPS. And you know this speed is sometimes called the synchronous speed. Synchronous speed. Why it is called synchronous? Because for a given machine it depends on the supply frequency. Supply frequency is constant. So supply frequency with in tune with supply frequency, this speed is decided, gets decided. Of course, for one 4-pole machine, 2-pole machine, it will be different. And you can tabulate this for a given machine, 3-phase machine. These things you should be at your fingertips. That is, suppose if P is number of pole 2, this synchronous speed, and let us write it in RPM, which is much this way it is used. So this into 60 once again. So for 2-pole machine, what should be the synchronous speed? 3000 RPM. 3000 RPM. For 4-pole machine, 1500 RPM. This should be at your fingertips. You should remember this. 6-pole, 1000 RPM. Like that. One can go on. One can go on. And another thing you should remember, that suppose henceforth what I will do, that suppose a structure is there, rotor. It houses a 3-phase winding. It houses a 3-phase winding. And from the rotor, how the terminals are accessed? Suppose through slip ring and brushes, these terminals are brought out. And you have energized it with 3-phase supply, and 50 hertz. And suppose the number of poles of the machine is 6 pole. The rotor may be driven by an external agency at a speed of, say, 750 RPM. In this direction, 750 RPM. This rotor speed, whenever I am telling with respect to obviously a stationary observer. That is, with a tachometer I measured the speed of the rotor, mechanical speed, with respect to stationary observer. Please calculate that is, if the observer could see the field which is rotating, at what speed he should have seen that field. Then there may be two situations. You should argue like this. Rotor may rotate along the same direction as that of the field, along the other direction. So today I conclude here, and tomorrow I will continue.